or the beginning of tomorrow's class. Okay, sir.
Okay.
Okay, sir. Okay, sir.
All right.
So is it
So,
fine, sir, to leave out 30
yeah,
minutes?
yeah, yeah.
Okay, okay, fine, fine.
Okay. Good morning, everyone. So we have started recording. Um, okay. So our we are continuing our discussion on planarity and connectedness, three connectedness. Okay. Our first goal is to prove that simple three connected planar graphs have a unique planar embedding up to facial isomorphism. Okay. But before that, I think that there is some misconceptions regarding what facial isomorphism means. Okay, so I want to quickly revisit facial isomorphism because I got a few questions that indicated that there was some misconception regarding the same. Okay, so let's go there. Okay, so we are back to few lectures ago when we defined facial isomorphism. Okay, so here is the way to think about it. If you look at two planar embeddings of this graph that you see on the left side, right? So it's two triangles, 1, 2, 3, 4, 5, 6, joined by three edges, 1, 4, 2, 5, and 3, 6. That's our abstract graph, right? So there are two planar embeddings given here. Why are they facially isomorphic? Well, you label the vertices as we have done 1, 2, 3, 4, 5, 6, and you check that each facial cycle, which means every cycle that is a boundary of a face in the first graph, is also a cycle that is a boundary of some face in the second embedding. Okay, we know the number of faces are the same by Euler's formula. So if every face in G1, every facial cycle in G1 is also a facial cycle in G2, then these are said to be facially isomorphic plane graphs. Okay. So what is a point I want to distinguish from? For example, this is not saying take the following graph. We are not just comparing if the boundaries of the faces are isomorphic to each other in the graph theoretic sense. Supposing I take this graph 1, 2, 3, 4, 5, 6. Um, okay, and now let me take a different embedding 1, 2, and what I will do is I will swap 3 and 4. Let's say I put 4 here, I put 3 here, I put 5 as it was, and I put 6 as it was. Okay, observe that in this plane graph 1 4 2 5, 1 4 2 5 back to 1 is a facial cycle, right? It is 1 4 2 5 back to 1. This is the boundary of a face. However, if you look at the same cycle here 1 4 2 5 1, this is not the boundary of any face. So it is not a facial cycle in the second embedding. Okay, and therefore these two G1 and G2 are not facially isomorphic, right? So the labeling of the vertices is important, otherwise I can't even compare the two drawings in that sense. Okay, so you need to label the vertices. More importantly, the edges, especially if you have multiple edges, then you actually have to be careful about which edge you are looking at, right? But once you label the vertices and the edges, you basically compare all the boundaries of the faces, right, as subgraphs. And if they are the same subgraphs, then you say that the two are facially isomorphic. Okay, what is a misconception that was going on? Notice that all the faces here, the boundary of each face is a 4 cycle. Each facial cycle is a 4 cycle. Okay, and that is the same here. Even in this drawing, each facial cycle is a 4 cycle clearly, and there are 4 faces in each of them, which is invariant by Euler's formula. That does not mean that the two graphs are facially isomorphic, right? It is not about just checking whether the boundaries of the faces uh, comprise the same kind of graphs up to isomorphism, right? So they are all 4 cycles. That does not mean that they are facially isomorphic. Okay, is it clear? Are there any questions or concerns regarding facial isomorphism?
Sir,
Yeah.
so facial isomorphism is like a stronger notion of graph isomorphism, right?
Yes, it is.
Okay.
It is. Yeah. Yeah. So that was one of the questions towards the end yesterday. And yeah,
Okay.
it is definitely a stronger notion. Okay. Good. Any other questions or concerns? In fact, it's not a standard terminology. I just introduced it so that I can talk about things more precisely without using 100 words each time, right? So that's why I introduced this term. Okay. Good. So that is what we mean when we say that any three connected planar graph, simple three connected planar graph, has a unique planar embedding up to facial isomorphism. So you take any embedding, label the vertices. Because the graph is simple, it doesn't matter. You don't need to label the edges if you like. And now you take another planar embedding and observe that every facial cycle in the first planar embedding is also a facial cycle in the second planar embedding, and vice versa, which follows because the number of faces are equal. Okay, good. So that is what we are trying to prove. And our plan is to show that this topological notion of a facial cycle, because to talk about facial cycles, you need an embedding, is equivalent to a graph theoretical notion which does not depend on the embedding, right? And that is called non-separating cycles, right? So they are cycles that have exactly one bridge. Okay. Um, yeah, sorry, that have at most one bridge. So it could also be zero bridges, which basically happens when your whole graph is just a cycle. Okay, so not very interesting. Okay. Good. Also, how did I define a facial cycle? I think I required the graph to be simple three connected. That is not necessary. I'm going to change the definition slightly. For a plane graph, um, any cycle that is the boundary of some face is a facial cycle. Okay, you don't need the graph to be three connected to talk about facial cycles. You just need a planar embedding. Okay, and we already know that in the case of non-separating graphs, every face is bounded by a cycle, right? So all the boundaries basically correspond to facial cycles once your graph is non-separable. Okay, so the reason I wanted to generalize this definition is because I realized last night while thinking about things that one of the directions of this theorem does not require simple three connected plane graphs. Can somebody tell me which one is that direction? So we want to prove this theorem, but one of the directions is actually a more general statement. Anyone?
So I think it would be facial implies non-separating.
Facial implies non-separating. If the cycle is facial, uh, hmm, I'm not too sure. Why is that true? Supposing the cycle is facial, then why is it non-separating?
So by non-separating, we mean the cycle C has exactly one non-trivial bridge.
Yeah, but go to that example, right? So I'm saying that the easy direction does not even require the graph to be three connected, right? So consider this facial cycle, the boundary for this face, right? This has two bridges. Do you agree?
Yes.
Right? So this is a facial cycle that is separating, right? So it's the other direction.
Okay, okay. Yes, 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 yes.
Okay. So it's the converse direction. Supposing you take a non-separating graph, non-separating cycle in a plane graph. Okay. So what is the easy direction? G is a plane graph. Let's say C is a non-separating cycle. Okay. What does it mean? In our planar embedding, which is the graph G, we have this cycle, which is a simple closed curve, right? Something like this. Because this is non-separating, what does it mean? How many bridges does it have?
One bridge.
One or zero, right?
Uh,
Well, whatever the case, that bridge is either drawn inside or outside. So let me assume that the bridge is drawn inside. Assume without loss of generality that C has one bridge or zero bridges, and that is an inner bridge. Okay, so it is drawn inside, something like this, whatever. The point is, the outside face is bounded by exactly this cycle C, and therefore C is a facial cycle, right? This implies that the um, unbounded face is bounded, it is unbounded but bounded by, well, maybe I'll write, it sounds a bit strange to say this. Unbounded face has C as its boundary, right? And therefore, C is a facial cycle. Okay. So whenever you have only one bridge or zero bridges, clearly you will draw that bridge inside or outside, and then the other side would be bounded by the cycle C itself, and therefore C will be a facial cycle. Okay. So that is the easy direction. It is really the converse direction, or in this case, the forward direction, that requires the graph to be simple and three connected. Okay. So we want to prove that if a cycle is facial, then it is a non-separating cycle. Okay. So G is simple three connected plane graph. Okay. And let's say C is some facial cycle of G. Okay. Well, because it is a facial cycle, either all the bridges are drawn inside or all the bridges are drawn outside, right? Otherwise, it will not be a facial cycle. This implies that um, without loss of generality, C has no outer bridges. Okay, so all the bridges have been drawn inside. Okay, and our goal is to show, so every bridge is an inner bridge, and our goal is to show that there is exactly one inner bridge, right? Since the graph is three connected, it cannot just be a cycle because cycles are not three connected. Therefore, it has at least one bridge. Since G is three connected, the cycle C has at least one bridge, right? And another point is that all bridges of C are inner bridges because we assumed that there are no outer bridges since it is a facial cycle. Okay, so there are bunch of bridges and they're all drawn inside. Our goal is to show that there is exactly one bridge. Okay, so how do we proceed? Let's take a trivial bridge first. Supposing C has a trivial bridge, we will actually show something slightly stronger. It's exactly one bridge, and this bridge is non-trivial. Okay, so supposing there is a trivial bridge, let's first get rid of this case. What does a trivial bridge look like? Because the graph is simple, it has to be a chord joining two non-adjacent vertices of the graph. First, suppose C has a trivial bridge xy. Okay, E equal to xy. All right, so now we want to show that this graph has a two vertex cut. This is a three connected, this is supposed to be a three connected graph, right? Can somebody explain where is a two vertex cut here? Does anybody see a two vertex cut?
X and Y.
X and Y, exactly, right? Why? Why is X and Y a two vertex cut? Claim XY is a two vertex cut. You see, if you look at any bridge in the graph, the bridge cannot overlap this bridge, the edge E equal to xy, right? Because inner bridges cannot overlap. This is one of the theorems, this is one of the observations we made earlier when we talked about bridges, right? So for every bridge, it has to avoid the bridge that we have already drawn. What that means is that if you look at any bridge, all of its attachment vertices will have to be either on this path joining x and y, or it will have to be on this other path joining x and y, right? The cycle has two paths, p and p prime, joining x and y. Each bridge's attachment vertices will have to belong to these paths, right? Also notice that a cycle plus one edge is not a three connected graph. You will have vertices of degree 2 because the cycle is length at least 3. So there is at least one more bridge in the graph. Let's say this bridge is called B1. Okay. And let's assume that all the vertices of attachment of B1 lie on the path P. Then I claim that when you delete X and Y, the vertices of B1 can no longer reach the vertices of P prime, which are different from X and Y. Okay. So that's the argument. I'll just say that complete argument yourself. Okay, it's right, but this is basically what we discuss is basically the whole argument, right? So if you delete x and y, the vertices of B1 will be disconnected from the internal vertices of P prime, and therefore xy is a two vertex cut. Okay, are there any questions or concerns? All right, so we don't have any trivial bridges. So C has only non-trivial bridges. Okay, and we want to show that there is exactly one of them. Okay, so let's suppose there are at least two non-trivial bridges. Okay, for the sake of contradiction, B1 and B2. Okay, because they are both inner bridges, so maybe this one I'll write down. So suppose C has at least two non-trivial bridges, say B1 and B2. Okay, because they are both inner bridges, they must avoid each other. By observation made earlier, B1 and B2 avoid each other. What does that mean? That means that if you look at the vertices of attachment of B1 and B2, then all the vertices of attachment of B2, they belong to a particular segment of the cycle induced by the vertices of attachment of B1. Okay, so let me remove these P and P prime, and let me call this P. Um, and maybe I will keep X and Y as these two vertices. This implies, by definition, that all vertices of attachment of B2 belong to a particular segment of the cycle C induced by the bridge B1. Let this segment be called, say, P with ends X and Y. Okay? So all the vertices of attachment of B2 have to belong to this segment. It could look like this, for example. I claim that there is still a two vertex cut here. Can anybody tell me what is a two vertex cut?
X and Y again.
It's once again X and Y, right? If you delete X and Y, then B2 and all the vertices of P distinct from X and Y will be separated from the vertices on the other side. So let's say this side is called P prime as before, right? Let C be the cycle which is a union of paths P and P prime, such that P prime is an XY path, right? So now it's clear what the definition of P prime is, but a bit cryptic way to write it, but anyways. Okay. So now, once again, XY is a two vertex cut in the graph G. Okay. All right. So that's it. In any case, you will get a two vertex cut, which is a contradiction because our graph is three connected. So we are crucially using three connectedness, which was not the case in the easy direction. The easy direction did not depend on three connectedness, right? All right. And the point I want to make again is that this proves that planar embeddings of three connected simple planar graphs are unique up to facial isomorphism because the facial cycles are exactly the non-separating cycles, and non-separating cycles does not depend on the embedding. It is a graph invariant property, right? It does not depend on the embedding that you're looking at. Okay, so that's it. And this proves this theorem. Okay. Any questions or concerns regarding this theorem or anything we discussed so far? We also use the property that the graph is simple because often we made claims like, first of all, the cycle is not just two edges, right? It's a cycle of length at least three. And then we use the fact that the graph has at least three vertices in some places, but that may have been more subtle. So maybe you can go through the proof again to check that, right? So you really need the graph to be simple and three connected. Okay, but I want to continue with planarity's deep connection with three connectivity. So our first point was to prove the uniqueness of planar embeddings. But there is another point I want to make, which is that in order to prove Wagner's theorem, we can restrict ourselves to three connected graphs. Reducing, let me call this reducing Kuratowski or Wagner to three connected graphs. Okay, so we will prove that if we prove Kuratowski's or Wagner's theorem for three connected graphs, then we prove it for all graphs. Okay, that is what I mean by reducing.
Sir, I'm leaving.
Okay, see,
Leaving, sir. Okay,
thanks.
well.
Yeah, all right. So so I want to start with some observations that we have probably noted earlier. First of all, a graph is planar if and only if its underlying simple graph is planar. Okay, so this proves that we don't need to worry about all graphs, we can just look at simple graphs. Okay, in fact, I'm going to say simple three connected graphs. That is where we are going. Secondly, this is quite clear to see. A graph is planar if and only if each of its components is planar. Right? So that reduces the problem to connected graphs, which is almost always the case in any problem we look at. And thirdly, a graph is planar if and only if each of its blocks is planar, right? So if you have a separating vertex, then at that separating vertex, you can stick the two planar embeddings and get a planar embedding of the bigger graph. Okay, that's basically the idea. So at this point, the problem has been reduced to two connected, or if you like, non-separable simple graphs, right? So, so far, we have reduced the problem to simple two connected graphs. Okay. And now we need to go one step further to reduce it to three connected graphs that are simple. Okay. So there are some simple lemmas we need, and that's it. And tomorrow we will prove Wagner's theorem for three connected graphs, simple three connected graphs, and that will be the end of planarity. Okay, and we'll move on to vertex colorings from Monday. So that's the plan for the next 90 minutes or so. Okay, so supposing you have a graph G with a two vertex cut xy. Okay, then I want you to remember marked components, the marked xy components. So we have x and y, and you have a bunch of components. Let me just draw two components for the sake of illustration. Okay, so what are the marked xy components? You take the component along with x and y, you take the induced subgraph, and then you add an extra marker edge joining x and y. So this edge is called the marker edge. Okay, and this is a marked xy component. So the claim is that the graph is planar if and only if each of its marked xy components is also planar. Okay. All right. So this one is not difficult to prove, and it will require one lemma. So the proof is do it yourself using the next lemma. But intuitively, it seems it should be true, right? So let me state one more lemma that is also not difficult to prove. This is 10.33, my bad. Okay. So once again, let's say we have a graph G with a two vertex cut xy. Okay. Then the claim is that if you look at any marked component of this graph, marked xy component, then it is a minor of the big graph. Each marked xy component of G is a minor of the big graph G. Okay, let me give you one example to explain what this means. Supposing my graph looks like this. Okay, so let's look at one of the marked components. One of the marked components is this side along with the marker edge. I claim that this graph is actually a minor of this graph. In fact, I think we can prove something slightly stronger. We can basically replace this edge by a path going from x to y on the right hand side. So we will actually get a subdivision, and that will imply that it is also a minor. Okay, so how do we do that? Well, let's look at the same stuff here. So we have these edges. What we don't have is this marker edge, right? But that's okay. I can replace the marker edge by taking a path between x and y on the other side. I don't know, whatever, some path, right? So if you take all of the curvy black stuff and the blue stuff, what you have is a subdivision of this graph, J, which is a marked xy component of the big graph, and therefore J is a minor of G, and G is this graph. Okay, that is basically the proof on an example, and you can generalize it to any graph by following this idea. Okay, is it clear what the statement is saying?
So can I
Are
scroll
they?
up and
Yeah,
show it
sure.
again?
Yeah.
Okay.
Yeah. Okay. So even this lemma, I'm not going to write down the proof. I have shown it to you on one example, and you just need to generalize it to all graphs. But it's the same idea that we used on this example. Okay. So once again, do it yourself. So now let's try to see why this lemma would imply the above lemma. Um, okay. So supposing my graph is planar, and let's say one of the marked components is non-planar, right? But the marked component is a minor of the big graph. So you have a planar graph with a non-planar minor. That is a contradiction to things you've already observed. If a graph is planar, all of its minors have to be planar, right? Okay. So that basically proves one direction. You can try the other direction yourself. Okay. Good. So what's next? Okay, so I want to explain to you or just convince you that once we have these two lemmas, we we have actually reduced the problem to three connected simple graphs. Okay, so let's see why. So let's say we are trying to prove Wagner's theorem. Okay, we already know by our previous discussion that we can assume our graph is simple and two connected, right? So let's say G is a simple two connected graph. Our goal is to show that if G is non-planar, then G has K5 or K33 as a minor. That is a difficult direction of Wagner's theorem, which is what we need to prove because the easy direction we have already proved before. Right? So to prove if G is non-planar, then G has a K5 minor or a K33 minor. Okay. All right. So supposing the graph is, and we are going to assume that we have already proved the statement for three connected graphs, which we are going to do tomorrow. So I want to convince you today in the remaining 7 minutes or so that if we have proved the statement for three connected graphs, then we have also proved it for all graphs. Okay. So assume true for three connected graphs, right? Good. So if your graph G is not three connected, then it has a two vertex cut. Suppose G is not three connected. This implies G has a two vertex cut XY, right? Because the graph is non-planar, by lemma 10.34, one of the marked components will also have to be non-planar, right? If the graph is non-planar, then at least one of the marked XY components is non-planar, is the same as what we have written down here. So by lemma 10.34, at least one marked XY component, say J, is non-planar. Okay. We are proving by induction. So I should probably say that we are proving by induction on the number of edges. Okay. And the base case is three connected graphs. Okay. So in this case, we have gotten a smaller graph J. Note that the number of edges of J is always less than the number of edges of the original graph. Is that true? Right. That is true because you'll have at least one edge on the other side. Right. So that will be true. So you have a smaller graph that is non-planar. By induction hypothesis, this graph will have a K5 or K33 minor. J has a K5 or K33 minor. But remember, J itself is a minor of the graph G. That is lemma 10.33. Every marked component is a minor of the big graph. It is isomorphic to a minor of the big graph. Right. So by lemma 10.33, J is a minor of G, right? Which means you can obtain J from G by deleting edges, contracting edges, and deleting vertices, right? Okay. So J is a minor of G, but K5 or K33 is a minor of J. Oh, maybe transitivity holds for minors. And then we would be done. So that is true. And that is another small 2 years of exercise. Transitivity of minors. So prove that if H is a minor of G and J is a minor of H, then J is a minor of G. Okay? So if that is true, then K5 or K33 is a minor of the big graph G by transitivity. Sorry, K5 or K33, G has a K5 or K33 minor. Okay. Good. And that would be the end of the proof. So what is missing? The only thing missing now is the base case, which is proving the statement for simple three connected graphs. Okay. And we've already reduced the problem to simple graphs, so that's fine. Okay. So tomorrow, which is our last lecture on planarity, proof of Wagner's theorem for three connected graphs. Okay. We have another 1 or 2 minutes, so I'll just tell you what the main ingredients are. And those of you who are inclined, you can try making progress on your own. Okay. So one of the things we are going to use is Thomason's result from connectivity module, which is that in any three connected graph on at least 5 vertices, there is an edge that you can contract and get a smaller three connected graph. Okay, so the ingredients, the main ingredients, one is Thomason, which basically says that there exists an edge E such that G contract E is also three connected, right? So you can apply, you can use this as an induction tool. This is the induction tool for proving for three connected graphs, right? And the second main ingredient is the theory of bridges. Right? So what happens is you have some non-planar graph, you contract a particular edge E equal to xy, and you get a smaller graph. Which is again three connected. So all of its neighbors will lie on some cycle. That is another result we proved at some point. There is one more ingredient. In a three connected plane graph, in a three connected simple plane graph, I don't know if we even need simple. We don't need simple, I think. In a three connected plane graph, all neighbors belong to a cycle. Right? So all the neighbors of this contracted vertex, this vertex resulting from contracting the edge E, they will lie on some cycle. And now you go back to the original graph by expanding this vertex. Okay? And you think about the bridges of this cycle, Um, and then you use the theory of bridges. Anyways, I won't tell you too much more. Now you can try on your own. Okay. Anyways, there are a bunch of ingredients, but I would say that in some sense, the main ingredients are these, right? Okay. All right. So that is the end of today's lecture. But if there are any questions or concerns, I'm here for another 5-10 minutes. So feel free to ask.
Sir, can you show lemma 10.33?
10.33. Yes, here.
Okay.
Yeah. Okay.
Sir,
Yeah, go ahead.
so for the proof of the theorem, will something like this work? So in the contracted graph,
Okay.
like
Okay. So let
by
me just stop
induction.
recording. Let me stop recording the
Okay.
meeting because I think everybody else has left.